Hey everybody, and welcome to our very first number theory lecture. To get things started off on the right foot, let's just go over a few concepts that we're probably familiar with, but we got to start somewhere, so let's start here. Let's look at the sets of numbers that we'll be dealing with frequently. First, we have the natural numbers, denoted by a bold-faced capital N. And what these are the positive counting numbers. 1, 2, 3, 4, 5. The natural numbers are the positive counting numbers. And I will tell you this. Some people will define the natural numbers in a slightly different way. And the difference is that some people who define the set of natural numbers will have 0 as the first natural number. For the most part, we will say that the natural numbers are the set of positive counting numbers. But when it suits our purpose, we will allow 0 to be a member of the natural number club. So unless otherwise specified, it's the positive counting numbers. But if it suits our purpose, we will give 0 the privilege of being a member of the natural number club. The next set that we're going to look at is the set of integers. And the set of integers is denoted by a bold-faced capital Z. The integers are the set of all whole numbers, positive, negative, and 0. So it contains the negative whole numbers, 0, and the positive whole numbers. And I guess we could also represent the set in roster form this way as well. Number theory is essentially the study of natural numbers and integers. We very rarely go outside the set of natural numbers or the set of integers. We might, once in a blue moon, talk about the rational numbers in this course. Very rarely. But we will define the rational numbers. The set of rational numbers represented by a bold-faced capital Q is the set of all real numbers that can be expressed as the quotient of two integers, of course, where the denominator is not 0. So the set of rational numbers is the set of all real numbers that can be expressed as the quotient of two integers. And again, in number theory, we very rarely ever think about or give consideration to the rational numbers. I'm defining the rational numbers right now just in case that rare situation comes up when we need to consider rational numbers or properties of rational numbers. But by and large, and when I say by and large, I'm talking about 99.9% of the time, number theory has to do with the study and properties of natural numbers and integers. Now might be a good time to introduce something that we've probably never seen in any other course. We'll use it in number theory, not frequently, but we will use it, and we'll use it in situations where we have to prove something and there just doesn't seem to be any other way to prove it than to use this thing called the well-ordering principle. We're not going to use it every day. We probably won't use it every other day. Maybe on average about once a week. but it comes in handy in proving some things that we'd be hard-pressed to prove otherwise without using this. And here's what it says. Every non-empty set S of non-negative integers contains a least element. Now, there are two conditions here. First of all, the set S has to be non-empty. If the set S is empty, it can't have a least element because it doesn't have any elements at all. So first of all, in order for the well-ordering principle to apply, the set S has to be non-empty. The second condition necessary for the well-ordering principle to apply is that all of the elements in the set S have to be non-negative integers. Not just integers and not just non-negative, but they have to be non-negative integers. So every non-empty set of non-negative integers has a least or a smallest element. And what we mean when we say that it has a least element is that there is some unique element in the set S such that, and we'll call this A, there's some unique element A in the set S such that A is less than or equal to every other element in the set. This is our least element. Every other element is greater than or equal to this element. Now let's look at some examples of where the well-ordering principle applies, and an example where it doesn't apply. Okay, let's look at this example. S is the set containing or consisting of integers that are the square of an integer. So every element in this set is the square of an integer. First of all, S is a non-empty set. And as an example, 25 would be in this set, wouldn't it? Because 25 is the square of both 5 and negative 5. So 25 is an element of the set S. So S is a non-empty set of 2 non-negative integers, and I guess the second one is kind of a no-brainer. The square of any integer. No, I don't want to say that. I want to say the square of all integers is non-negative. S is a non-empty set. For example, 25 is an element of this set of non-negative integers because the square of every integer is non-negative. Because of this, the well-ordering principle guarantees that S has a least element, an element that is less than or equal to all other elements of the set. And that least element is 0. 0 is the square of an integer, right? 0 is its own square. 0 is the square of an integer, and this is the smallest non-negative number that there is. So this is the least element of the set S. S was a non-empty set of non-negative integers. The well-ordering principle guaranteed that it had a least element, and here it is, 0. Let's look at another example. Maybe the next one won't be quite so trivial. And then again, maybe it will be. Another example. We have the set P. P is the set of amounts of postage that can be paid using 3-cent and 7-cent stamps. P is non-empty. For example, 10 is an element of set P. We can pay 10 cents of postage with 1 3-cent stamp and 1 7-cent stamp. So P is non-empty. The second thing, P is a set of non-negative integers. There's no such thing as a postage of negative 3 cents. Therefore, by the well-ordering principle, P has a least element. Now, what is that element? It all depends on who defines the rules of this game. Are we going to say that free postage is postage that we pay? I guess I'll make up the rules and say no, postage has to be something that we pay. So P does have a least element. We can pay 3 cents postage with a 3-cent stamp, and that makes 3 an element of this set P. Again, P was a non-empty set. For example, 10 is an element of P. P is a set of non-negative integers. No such thing as negative postage. So by the well-ordering principle, P has a least element. It's P. All postage that we can pay with 3-cent stamps and 10-cent stamps is greater than or equal to 3. So 3 is the least element. Now we'll look at a situation where the well-ordering principle doesn't apply. Another example. We'll let D be the set of integers that leave a remainder of 1 when divided by 5. Why did I call this set D? I don't know. When I was writing my notes, it seemed like an appropriate name for the set. I have no idea why I called it D. But D is the set of all integers that leave a remainder of 1 when divided by 5. So, does the well-ordering principle apply? D is a non-empty set. For example, 6 is a member of D. And we'll recognize that 6 equals 1 times 5 with a remainder of 1. So 6 is an element of D. When we divide 6 by 5, we get a remainder of 1. And let me make sure I'm consistent on my notation here. Not that it was bad before, but I want to write everything the same way. D is a set of positive and negative integers D is not non-negative. There, did I squeeze all that in? Ooh, I did. Good. D is not non-negative. And what did I use for examples here? Well, we noted that 6 was in D. 6 equals 1 times 5 with a remainder of 1. 11 is in D. 11 equals 11 equals 2 times 5 plus a remainder of 1, or 11 divided by 5 is 2 with a remainder of 1. But let's look at some shady characters that gained access to this set. Negative 4 is an element of D, because we can say that when we divide negative 4 by 5, 5 goes into negative 4 one time with a remainder of 1. Let's see, does that work? Negative 1 times 5 is negative 5 plus 1 is negative 4. Yep, that works. Negative 9 is an element of D. Negative 9 equals negative 2 times 5 plus a remainder of 1. Okay. And maybe one more, negative 14 is an element of D. Negative 14 is equal to negative 3 times 5 plus a remainder of 1, etc. Now we can keep on going. Just keep adding negative 5 to the most recent entry. Negative 19, negative 24, negative 29, negative 34. D does not have a least element. The well-ordering principle does not apply. Well, why doesn't it apply? Because D is not a set of, that's right, non-negative integers. So here's a case where the well-ordering principle doesn't apply, and because of that, the set D does not have a least element. Okay, on to bigger and better stuff. But this was something that we needed to cover. We're going to use the well-ordering principle to prove some non-trivial stuff. We're not going to use it every day, but maybe on average about once a week throughout the course. And the well-ordering principle will be very handy because it will allow us to prove some things that otherwise we'd be very hard-pressed to prove. You know, the opportunity to apply the well-ordering principle came a lot sooner than I anticipated. We're going to prove the Archimedean property. The analog of this, if we're talking about just real numbers in general, is sometimes referred to as the axiom of Archimedes. But here's the Archimedean property as far as integers are concerned. If A and B are positive integers, then there exists a natural number n such that n times A is greater than or equal to B. So no matter how much bigger than A B is, we can multiply A by some natural number so that we get a number that's at least as big as B, if not greater. And we're going to do this proof by contradiction. And when we do a proof by contradiction, we assume the exact opposite or the negation of what it is we're trying to prove. We're trying to prove that there is a natural number n that we can multiply a by to get something that's at least as big as b, if not greater. So to do a proof by contradiction, or to do this proof by contradiction, we're going to assume that there is no such natural number n that makes this happen. So for the sake of deriving a contradiction, we suppose that no such natural number n exists. There's no natural number that we can multiply a by so that we get something that's greater than or equal to b. Well, that's the same thing as saying that n times a is less than b for all natural numbers n. Okay. So if no such natural number n exists such that n times a is greater than or equal to b, then every time we multiply a by a natural number n, we get something less than b, no matter what that natural number is. Let S be the set of all numbers b minus na for all natural numbers n. So let S be the set of all natural numbers of the form b minus na such that n is a natural number. And we'll make some observations. First of all, note that S is non-empty. Well, let's see, how do we know that? S is the set of all numbers of the form b minus na, where n is a natural number. Okay, well, pick a natural number. Let's say n equal 1. Whoops. B minus 1a is in S because 1 is a natural number and it fits this form. So S is non-empty. Now let's make another observation. And that is that S is a set of non-negative integers Let's see, why is that the case? Every number in this set is of the form b minus na for some natural number n. But we've assumed that no matter what natural number n we pick, n times a is less than b. So na is always going to be smaller than b. So we take b, which is larger, subtract na, which is smaller, we get something non-negative. S is non-empty, and every element of S is non-negative by our assumption. We assumed that since no natural number n exists that makes n at least equal to, if not greater than b, that NA has to be less than b for all natural numbers. And if NA is less than b, b minus NA is non-negative. In fact, positive. Okay, let's see. What do I do now? Well, we've established that S is non-empty and that S is a set of non-negative integers. So we've set the stage to apply the well-ordering principle. So let's do it. So here's our least element, b minus MA, for some natural number M. There's our least element. And this is a proof by contradiction, which means that we're deliberately going to try to make things go wrong. We have a least element, which means this has to be less than or equal to every other element in the set. And we're going to try to make this mess up somehow. So to get our contradiction, we'll focus on another element. And what would that element be? B minus M plus 1 is also an element of S. Okay. Well, let's see. Why is it an element of S? Here's our least element. And M, since B minus MA is in the set S, M has to be a natural number, positive integer. So M plus 1 is certainly a positive integer, natural number. So this is B minus some natural number times N. This is in the set S, because S is the set of all numbers of the form B minus some natural number times A. Whoops, whoops, whoops. Pay no attention to the man behind that curtain. B minus M plus 1 times A. Please forgive me. B minus a natural number times A. This is in S. Okay. Well, we did this to make things go wrong. I'm kind of wondering what's going to happen here. But let's just work some things out and see if we can make something bad happen. here's the element that's going to save the day for us because it's going to make everything go horribly wrong. So let's pay attention to that. This element, b minus m plus 1 times a. Let me just distribute the a inside the parentheses here. I'm going to get b minus ma, and m times 1 is a minus. Okay. Now, what's significant about that? Well, here's the current least element. This is supposed to be the least element of our set S. Will this thing dethrone the current champion when it comes to being the least element of S? Let's put the two side by side and see what happens. B minus MA. Which one of these two is smaller? Well, let's see. B minus MA, B minus MA. To get this expression, we're taking B minus MA and we're subtracting something positive. Remember, A and B were both positive integers. So this thing has to be less than that thing. Okay. Now, just to make sure that we focus on what really went wrong here, notice that what we've just done is we've shown that this thing is less than that thing. Okay, yeah, so what's the big deal about that? Well, wait a minute. Wasn't this supposed to be the least element of set S? In other words, every other element of set S was supposed to be less than, or I'm sorry, wasn't this supposed to be less than or equal to every other element of set S? But here's an element of set S that's less than this guy. Okay. We just made everything go wrong, which is exactly what's supposed to happen in a contradiction proof. Now, usually in a contradiction proof, we stop when we get the contradiction and say, okay, we proved it. But let's really shine some light on what's going on. What is it that caused this contradiction? let's see. We assumed that there was no natural number n such that NA would be greater than or equal to B. That's what led to this train wreck. We said there does not exist an n, a natural number n, such that NA is greater than or equal to B. And this is the assumption that caused the contradiction. The assumption has to be false. This assumption has to be false because it led to a contradiction. And if this assumption is false, it must mean that the negation of that assumption is true. Hence, there does exist a natural number n such that n times a is greater than or equal to b, which is exactly what the Archimedean principle says. And that's the end of our proof. So we had an opportunity to use the well-ordering principle a lot sooner in this class than we might have expected. Excellent, excellent, excellent. We're going to be talking about the binomial theorem somewhere early in this course. So maybe now would be a good time to review factorials. No doubt we saw factorials late in Calculus 2 when we had to do Taylor series and Maclaurin series. And we may have seen factorials when we took a probability course, probability and statistics. Factorials often come in handy in probability and statistics. So we've probably seen we've almost certainly seen factorials. We may remember exactly what they are and be very familiar with their properties, or we may be a little bit rusty. So here's what we're going to do. We're going to define it and look at the properties and just play around with it for a little bit. This is, I think, the most intuitive way of looking at n factorial. N factorial is the product of itself times every positive integer less than n. And we'll look at a few examples. 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, etc. 1 factorial, well, this is a product of one factor. So 1 factorial is just going to be 1. Now let's go about this a little bit more systematically. 1 factorial, as we observed, is just 1. 2 factorial is 2 times every positive integer less than itself, 2 times 1. 3 factorial is 3 times every positive integer less than itself, 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. And we've probably noticed another relationship here. Maybe this would be a good place to start. 4 times 3 times 2 times 1. Well, what is 3 times 2 times 1? That's 3 factorial, isn't it? So 4 factorial is equal to 4 times 3 factorial. 5 factorial, if we look at that, look at these numbers right here. 4 times 3 times 2 times 1, that's 4 factorial. So 5 factorial is equal to 5 times 4 factorial. And let's see, it works up here too, doesn't it? 2 times 1, we say, that's 2 factorial. So we can write 3 factorial as 3 times 2 factorial. And if we extend this pattern backward, we'll look at this 1 and say, that's 1 factorial. So 2 factorial is equal to 2 times 1 factorial. Can we do anything here? Believe it or not, we can. Here's why. I'm going to insert something right here. 0 factorial. Well, wait a minute. Didn't I say earlier that n factorial is a function on positive integers? And n factorial is the product of the positive integer n times every positive integer less than n. This isn't a positive integer, so is 0 factorial really something that exists? And the answer is yes, and here's why. Mathematicians that came long before I was wearing diapers good mathematicians all recognized that arithmetic and algebra being done with factorials would work wonderfully if they would allow 0 factorial to exist. And you know what? This makes absolutely no sense, because here's what it was supposed to say. 0 factorial equals 1. And this is by convention. For no other reason other than a bunch of mathematicians decades and decades ago got together and said, you know what? If there was such a thing as 0 factorial, and we all agreed that 0 factorial equals 1, arithmetic and algebra with factorials would work wonderfully and everything would be consistent. And so they just adopted that convention. And we are proud to continue supporting and using and acknowledging this convention. And when we do, we can actually extend this pattern backward one more step. Whoops, I'm sorry. 1 times 1. Where this 1 right here is 0 factorial. So 1 factorial, we can say that that's 1 times 0 factorial. And we can write down this general algebraic property or arithmetic property about factorials. For all positive integers n factorial is equal to n times n minus 1 factorial. And this relationship even works when n is equal to 1. This is a very important property for us to recognize using factorials. So let's just acknowledge this right now and do some quick algebra, some examples, some quick examples. And for those of you that have had me as an instructor before, you know that sometimes before I show how things ought to be done, I show how things ought not to be done and why they ought not to be done that way. Especially when the most intuitive way to do something turns out to be incorrect. I'll focus on it and say, hey, see this? If there were any justice in this world, we ought to be able to do this, but we can't. It doesn't work. So let's acknowledge that it doesn't work. So we're going to look at some algebra using factorials. And we're going to look at some things that seem like they ought to work, but they don't. And then we're going to see what does work. Here's something that we're going to try something on. It ought to work, but it doesn't. What I'm thinking is cancel. Yep, yep. Divide top and bottom by 3 factorial. We get 2 factorial, which is 2 times 1, which is 2. Well, am I right? Let's see. 6 factorial over 3 factorial. What is 6 factorial? It's 6 times every positive integer less than itself. 6 times 5 times 4 times 3 times 2 times 1. And 3 factorial, that's 3 times every positive integer less than itself. Whoops. Well, we have 3 times 2 times 1 on top, 3 times 2 times 1 on the bottom. But ooh, we got 6 times 5 times 4, that's 120. 6 factorial divided by 3 factorial is 120. Ooh, my goodness. Now, it seemed like we should have been able to cancel like this, but we can't. And let's go back and see what I did that was actually incorrect. Let's analyze what I did and find out what it was that was incorrect. Here's what I did. I said, 6, there's a 3 in here. So 6 is equal to 3 times 2. 6 factorial is 3 times 2 factorial. And we got 3 factorial on the bottom. We can just cancel those. And we get 2 factorial, which equals 2. Now, let me just generalize what it was that I did. And by the way, before I go too far, let's make sure that we don't want to do what I just did here. I did this because it seems like it ought to work. It seems like the natural thing to do, but it doesn't work. And if we say the general case of this, let's say that we have m times n factorial, the factorial of this product, over m factorial. You know, I guess what I'm really thinking when I do this is that m times n factorial is the same as m factorial times n factorial. And then we can just cancel the m factorials. And we're left with n factorial. And again, I'll say, no, don't do this. And the error of my ways was this thing, this invalid assumption. And I guess, how would we say this? Was I assuming that the factorial can distribute over multiplication? I guess that's what I was assuming. It seems like it ought to work, but it doesn't. So in factorial arithmetic, let's not do that. Now let's do some things the right way using the definition of factorial and the property that n factorial is equal to n times n minus 1 factorial. Let's do some of those exercises, do them the right way. And we might just call it quits for today after that. Okay, let's do these the right way. And we're going to use the fact that n factorial is equal to n times n minus 1 factorial, which means that 8 factorial contains as a factor 7 factorial. So what do you think? Write the numerator as 8 times 7 factorial? That's right. 8 times 7 factorial over 7 factorial. And we can cancel equal things. And we get 8. Okay. Before we do this one, let's just do a retrospective of this. Notice what we did. We took the larger factorial and wrote it in terms of the smaller factorial. That's exactly what we're going to do here. 10 factorial is 10 times 9 times 8 times 7 times 6. Okay. 10 factorial is 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. So that's 10 times 9 times 8 factorial. And we can cancel the 8 factorials in top and bottom. And we get correctly that 10 factorial over 8 factorial is 90. Okay, one more for good measure. 8 factorial over 4 factorial. Again, we write the larger factorial in terms of the smaller factorial. 8 factorial is 8 times 7 times 6 times 5 times 4, 3, 2, 1. So 4 factorial. And the 4 factorials cancel. And holy moly, I have no idea what this should be. 56 times 5 is 280 times 6. Good grief. I think it's, yeah. 280 times 6 is 1680, I think. Okay, so we'll call it quits for today. And in the next lecture, we'll start out talking about propositions, and we'll cover weak induction and strong induction. Now, if you've seen induction before, but you don't know weak induction and strong induction, almost certainly weak induction is the kind of induction that you're familiar with, and strong induction is something that you haven't seen. But we'll take a look at both of these, and we'll do some nice things with some induction problems, because number theory is all about natural numbers and integers, and induction has to do with theorems which are about integers and natural numbers. So I will see you next lecture.